Hi apes. Today we're taking a look at Unit 9, Part 3, which is going to focus on stratospheric ozone. Now we've talked about ozone in the past. If you remember, ozone has a formula of O3. Now we talked about it in context of it being a pollutant in our troposphere. So we sometimes will refer to this as good up high, but bad nearby. Because in the stratosphere, it acts as a shield from UV radiation. And so there are three different types of UV radiation. UVA has a relatively long wavelength, UVB has a middle wavelength, and UVC is very tight. Now UVC is blocked by our atmosphere, and UVA is allowed to get through our atmosphere because of the wavelengths. But UVB should be blocked by ozone. But what we're seeing is that we're having an increase in more and more of our UVB radiation because of the thinning of our ozone layer. So more of our UVB is allowed to get through because our ozone layer is becoming depleted by CFCs. So remember, we talked about CFCs as a greenhouse gas in the troposphere. And one of the things about CFCs is that they're very, very stable and they have a long residence time, 50, 60 years CFCs. Now, when CFCs were developed, they were developed as both coolants or aerosols. And when they were first developed, they were like, oh, this chemical is so amazing, it doesn't react with anything. It's not going to cause any problems. But then they realized, this chemical doesn't react with anything and it's not going away. And then they saw that it acts as a greenhouse gas in the troposphere, still doesn't react with anything, and it makes its way up into the stratosphere where it damages our ozone layer. And so the problem with it being so long and stable means that it's available to make its way up to our stratosphere, and that's when UV radiation is the thing that really can break that CFC molecule apart. Now, we started to notice that our ozone was depleting sometime around the late 70s, early 80s. We do keep track of our ozone layer, the thickness of the ozone layer in our stratosphere, and we measure it in Dobson units. Now, our ozone is not very stable, and so it goes back and forth in this natural reaction all the time. O3 to O plus O2, and then back again in the presence of UV radiation. So up in our stratosphere, there's no shortage of that UV radiation. So this reaction goes back and forth, and it's in a natural balance. But what we started to see is that there was a decrease in the amount of ozone that we were measuring in October as we started to get to the 80s. So these bars show a statistical range that might be valid, and the point here is in the average. And so what we're seeing is that ever since around the 80s, it really did start to decrease in the thickness of the ozone layer and really started to get a lot of people's attention. So here is a graphic change of our ozone layers. So you can see that the purple means a very thin layer. Now we call this an ozone hole, but it is important to note that it's not a hole. We never have gotten to 0 Dobson units of ozone. It's just that it is thinner than it should be, and it doesn't allow the protection that our ozone layer does, remembering that ozone is there to protect us from that UVB radiation. So the ozone thinning occurs in a concentrated effort around our south pole for the most part, in Antarctica. You do see this as well in the North Pole, but it is concentrated in our south pole. And we'll talk about the reason why it is concentrated at the poles. But you can see that the ozone thinning does not take the same shape. It doesn't take the same severity year by year. We do always see the peak in October, and I'll be able to explain why. But just so you can see that it does vary through the years, and hopefully this is something that we are going to see begin to turn a corner, that we're not going to have this severe decrease in ozone anymore in the next couple of decades. So let's try to see why this occurs. Okay, so one thing we have to remember is that we are in the South Pole. We're in Antarctica. So our seasons are switched, which is why I say this is fall or winter and we're in April. Okay, so I'm setting the stage to lead us up to that October minimum when we see our least amount of ozone. So if we remember in our troposphere is where weather occurs. So you don't see a lot of weather in the stratosphere. But at the poles, the air is so cold and isolated that you can have polar stratospheric clouds form. So these are frozen ice clouds that will form. Because that air is so isolated, because there's that rotation of the earth, it creates a vortex that makes it very, very cool. So air is cold, it condenses and it forms these clouds. Now, because of the rotation of the earth, the CFCs that make their way to the stratosphere also become concentrated at the poles. And these CFCs become frozen and trapped on these clouds. So you have a high concentration of CFCs that are frozen on these polar stratospheric clouds. They're positioned at the poles and we're adding to the amount of CFCs that are trapped there. So this is going on through fall and winter. Now, as soon as polar spring happens, as soon as Antarctic spring happens, the sun comes out for the very first time, and that melts these clouds, and it releases the CFCs all at once. Because remember that in the fall and winter, the angle of the sun is such that that South Pole does not receive much light at all. And so this is the first time that UV light is hitting that area, warming those clouds, freeing that CFCs, and it is UV radiation that can react with that CFC. Now, CFCs are chlorofluorocarbons. Here's a carbon, it has a fluorine and three chlorines. Now, UV light will hit that CFC molecule and release a chlorine atom. Now, this is significant because remember we said that people were so excited about CFCs because they don't react with anything. And that is still true. CFCs do not react with anything, but chlorine is incredibly reactive. And it's the UV radiation that has the power to knock that chlorine atom off. And that chlorine atom will find an ozone atom, react to form ClO and O2. This O2 will go off into the atmosphere because this reaction is going on all the time. So it will find an O atom to join into. This ClO will find an oxygen atom that it gets from the surroundings. It's right here. And it will form ClO plus O, will react to form chlorine plus O2. And that will go off. Now this chlorine is free to come back and do it again and again and again. So we often call this a chain reaction because that one chlorine does not get used up. It just continues to hit more and more ozone molecules. So I'm going to show an animation of this to see if this helps to kind of cement this in your heads. So here we are up in our stratosphere. Here are the ozone molecules that are flying around.
Ultraviolet light hits a molecule of chlorofluorocarbon and breaks off a chlorine atom. The chlorine atom attacks an ozone molecule, pulling off an oxygen atom to form chlorine monoxide. A free oxygen atom pulls the oxygen off the chloride monoxide and releases chlorine. The chlorine atom is now free to attack another ozone molecule and begin the cycle again.
So I'm going to reset this just to talk through it one more time as it goes. So I'll pause at each of those reactions.
Ultraviolet light hits a molecule of...
So here's our first one where the UV radiation hits the CFC and frees a chlorine. The chlorine is going to then go find an ozone molecule for the Cl plus O3.
Chlorofluorocarbon and breaks off a chlorine atom. The chlorine atom attacks an ozone molecule.
So here our Cl hit that O3, created the ClO plus O2. So this goes off and joins into that natural equation.
pulling off an oxygen atom to form chlorine monoxide. A free oxygen atom pulls the oxygen.
So there's the ClO plus a free oxygen atom that's up there in the stratosphere because of that natural reaction, and it leaves this chlorine free to go get another ozone atom, or ozone molecule, excuse me. So this is to help summarize why we see it when we occur, that the peak happens in October, and where it occurs, why it happens at the poles. So the reason why it tends to happen at the poles is because that's where the air becomes isolated and cold enough to form those stratospheric clouds. So all those CFCs get concentrated. We don't see the ozone loss in the Antarctic winter because there's no sun to start that reaction. You need the UV radiation to release the chlorine. So you do see this happen all at once in the spring when the sun is releasing those chlorine atoms all at the same time and they're reacting with that ozone all at once. So you see this pattern throughout the year that you have no ozone loss because you don't have that release of the chlorine. And then all the chlorine does get released at the same time, reacts with those ozone molecules all at the same time, but it does recover because there's that background reaction of O plus O2 to O3 back and forth. So you do see a drop in October, but it will come back to recover when that chlorine does get used up and eventually rains out of the stratosphere. So the effects that we see from this loss of ozone is that there is a damage to food chains, because what you have happen is that you have an increase in UV radiation that might literally burn things like algae in our polar oceans, and it can burn plant tissues in general. So once you damage the base of the food chain, you're going to see the impact all the way up. You do see an increase in skin cancer. Now do be careful here. You have to be very careful that this is the only type of cancer that we can relate to increase in UV radiation. So this is occurring because we have more and more of that UVB radiation that we're becoming exposed to. That UVB also increases cataracts. So when it interacts with your eyes, it does increase cataracts, or the clouding of that lens. And because of that increased radiation, we are seeing cases of suppression of immune system as well. So these are both the environmental and the human impacts. So this is actually one of our environmental success stories globally, that we are seeing a reduction of the global emissions of CFCs. Now the reason we are is because of the Montreal Protocol. This is an international agreement that banned the use of CFCs. Now, because of the stability of the CFCs, even though they've been banned for a couple of decades, we won't see that decrease in CFCs in our atmosphere for about 20 more years because they are so stable. But we will see that reduction because CFCs are no longer being actively produced. Now, because it was such an important chemical, there are alternatives in HCFCs, and this replacement just expired in 2020 for developed countries. Because HCFCs, they are a little bit less stable, so they do cause less damage, but they do still act as a ozone depleting substance. So 2030 will still have a little bit, developing countries will still have till 2030 to phase out their HCFC. So this is like a temporary fix to try to find alternative, more expensive methods of using this chemical that did such a good job, particularly with coolants. But what this is a good success story that shows that when countries can band together, we have stopped and reduced the amount of CFCs. We are going to see this problem reverse, and we are going to have the benefit of less CFCs in our troposphere acting as a greenhouse gas.